Hi, good morning, everyone. My name is Ping, and this is Wei. We are data scientists at a security team at Salesforce. And today, in our presentation, Needle in the Haystack, we'll talk about several things. So first of all, the unique challenges like fighting cyber threats in one of the largest cloud computing platform, and our innovative and practical solution using behavior profiling and machine learning to detect anomalies. We'll also talk about the engineering architecture and implementation deployment of our solution in Apache Spark in production. Also, we'll demonstrate the efficacy of the method. So information security is hard, and it gets harder from the left to the right on the spectrum. In some cases, like we have partial or complete information about attack. So who they are, where they come from, or whose online credentials have been compromised. Well, in those scenarios, we can probably create signatures or rules to prevent or mitigate these risks. Or we can use correlation analysis to identify some unknown attacks, but with a certain level of intelligence or heuristics. However, in the most severe but very common scenario, we basically have absolutely no idea like what is going on, like when and in what form a business is being compromised. So these attacks are often called 0 days, and the persons who falls victim to those attacks are referred to as patient zero. The better we do well in the area of detecting these unknown attacks, the better chance we're against the most sinister adversaries. And our method, our solution we present today, focus in the last area. Information security is hard and super critical. It's always the top priority for Salesforce. So for the ones like who's not familiar with Salesforce, we are one of the cloud computing platform where various businesses, like from financial institutions to healthcare, hosting their business logics on Salesforce. So we have sales, marketing, customer service. We have all kinds of business logics like running on a Salesforce platform. So no surprise, we have a wide range of security threats to protect against. Those include account takeover, data exfiltration, or insider threats. So our solution works at the application layer in the cloud, and we work with user behavior events at the application layer. The reason being, application layer is one of the last and critical detection locations in the cloud. Unlike infrastructure or endpoint protection, once the attacker gets into the application layer, then there's pretty much not so much mitigation we can do without monitoring user behavior. So also the application layer has the complete context about a user interaction and enhance the information about user. So we can leverage such information to understand what user is doing and why they are doing certain weird things. In our model, we track several categories of user behavior characteristics, and those include who they are, where and from where they log in, and what actions they performed on the platform, as well as like how they did it. So these are some examples of the features we're tracking, and quite straightforward and generic here. Our solution works in the application layer. That being said, the solution itself is generic and general enough that can be applied outside of the application layer. So in modeling user behavior, we have some unique challenges. First of all, the size of data. We have 6 billion transactions on the platform on a daily basis. Also, the speed to response, because in the security world, you do not want to discover any attack like half an hour or even a day later. So those are definitely challenges, but somehow resolvable via tools like Spark or top-notch computing resources. At the same time, the attack forms we're targeting are in various forms and entirely unpredictable type of attacks. So with these, we do not have much of ground truth to work with at all. At the same time, among the many features we're tracking, how do we know which features are the most useful and the most indicative attack? And feature selection has been straightforward in supervised learning, but because we do not have ground truth to work with, we basically are in the unsupervised learning territory. Well, the most challenging thing has to be user behaves, quite unpredictably, and they change their behavior fairly often. Very often, like a new behavior that is for legitimate reason can be mistaken as anomaly. So we're constantly dealing with volumes of false alarms, and the method has to be smart, intelligent, and adaptive enough to address such user behavior novelty. So in summary, we formulate our solution as a combination of techniques. That is statistical modeling, behavior modeling, anomaly detection, and unsupervised learning. So next way, we'll talk about how we implement this method and address all the challenges about.
Yeah, sure. So recently at Salesforce, we have developed our anomaly detection engine, which is at user level. So this engine actually mainly have 2 modules. So the first module we call the profile building module, and the second, which is the actual detection. So the most expensive part, which is the profile building. So in this module, actually, we scan all the data under some time window, and to learn the user, to establish the user distribution by using some simple statistics. And at the same time, we will learn which features are relevant for this particular user or organization. And after we build all those profiles and then we store it in HDFS, and this basically the stage 1 you can think about this is training period. So we need a bunch of data to learn how the user behave, right? So once we establish those user behavior and also all the information about what feature are useful for this user, and then we store at HDFS. And during detection, in the detection phase, and then we just load all the profile and also those information and compare the current user behavior with all the historical behavior and to looking for a huge, large deviation. And with those, so of course, and following this detection, we will find out the any user and user activity. So regarding the feature selection, so it's quite challenging in anomaly detection, right? So because in anomaly detection, we have no labels. So how do we know, which feature subset is useful? So we think about use PCA. So we use PCA, we leverage PCA, the principal component analysis, to categorize all the raw feature set into 2 categories. So the first one, is high variance variable. So this is no surprise. So this is what people usually do in dimension reduction, right? So you're just looking for a subset of feature, and they can explain a majority of a variety and consider that's representative of a raw data set. So that's what high variance variable means. The interesting one, which is low variance variables. So and this is basically interesting in security domain. So example will be like, for example, a particular user always, during our profiling window, always use the max as operating system, right? So that one dimension doesn't change at all during the profiling. And suddenly, during detection, it uses, like, for example, Windows, a different operating system. So the user changed has a very large change along his very stable behavior dimension. And then that's one we try to catch in security, because actually that's kind of low-hanging fruit, right? You are stable and suddenly you change from your stable behavior, then we expect you are a different person using this account. So that's why we use PCA to do feature selection for our anomaly detection engine. And after we build that PCA mapping matrix to know the variance of each feature, and then we actually map all the raw feature into the feature subset, and actually build a profile along those in those feature subset. And here is quite important because when we think about this anomaly detection engine, the ideal case, we want to at least near real time or even real time detection. So with that requirement, we want, during our training, we really want very simple statistic to describe the user historical behavior distribution. So after some research, we finally decided to use those three simple statistics to describe each user behavior. So the first one, the first statistics, we established the user baseline behavior. So basically, we optimize the sum of distance for that. We first select all that user behavior, map to some numerical space, and minimize by minimizing the sum of distance, and to select the centroid of that all user data, and consider that is the user baseline. So all the user activity is around that area. And then we compute the variance of other data point that user other data point with the centroid, and to see what's the distribution looks like, the variance. And with those two, so here in our user application level anomaly detection, one of the things we suffer a lot, which is the false alarms. Why is that? Because sometimes in application layer, user himself will do some non-typical stuff, right? So you random click something and you will do some non-typical stuff. And in order to reduce that false alarm, so we also, besides the user baseline, we also need to establish what's the user non-typical behavior. So as you can see from the red chart, so all the blue points, actually that user's behavior in the profiling window. So clearly there are two clusters, and we see this quite often across many users. So there is one very dense area, which is the lower end, there are blue points. It seems only one data point, actually there are hundreds of data points, all in that very dense area. And there are 5-6 blue points on the right-hand side. That's the user's his own non-typical behavior. And we capture that. So we capture the distribution of those two clusters. So you can think of in the profile building at each user, we just the assumption that there are only two clusters. One which is your majority behavior, the other one which is your non-typical behavior. So we calculate those three statistics to describe each user. So this is basically what's the detailed architecture in the profile building module. So we have some raw events, right? We do some simple feature engineer, clean the data, parsing the data, and transform the data. And then we will build the PCA mapping matrix at certain level, and then with those mapping matrix, we're going to map the raw feature into two feature subsets, which is high variance and low variance. And we will build separate profiles along those variants. So, which means we describe each user from two perspectives. So one is from your, we want to look at how this user behave along his stable behavior. And the other profile is just try to look at the hard, those features with high variance. Those basically the raw, the representative of the raw dimension. So, and then we store all those profiles and the mapping matrix at HDFS. And then in the detection period, and then for each user current behavior, then we just compute the delta, right? We want to see whether you have a large deviation. But here is quite important. So as I mentioned before, so we build a profile, and right now we have two coming user events. Those two red points are from this user. And both those two has very large deviation from this user's baseline. But we are not necessarily assigned the same anomaly score. So because our model will, each day will generate a certain amount of alerts, and we will hand off these alerts to the human analytics, right, for them to do further investigation. And we need to give them a priority, which one they should investigate first. So the way we set up the priority is that we will have a correction score. So if the large deviation point is close to this user's previous non-typical behavior, then we will lower that anomaly score. So here it's important. We don't exclude that red point. So we just rank it lower. Say, we need to give a priority. Say, this is still a euro, but not as important as the red point in the upper left, because that's something, large deviation, also not something I have seen before for this particular user. So this is kind of overall architecture in our detection module. So as I mentioned before, so we built two types of profiles, right? One for low variance and one for the other one is for high variance. And we believe that actually when we deploy this, we find out like the anomaly along the low variance is more, has super high priority, because you suddenly change has large deviation from a stable behavior, should immediately investigate what's going on, right? So it's kind of a hierarchical chain architecture. So we first look at whether you deviate from your very stable behavior. If it's yes, then we immediately investigate that. If not, then we pass to the high variance profile and then see whether you have deviation on that dimension. So we have this model, and we try to evaluate it. So we need to see how well it performs, right? So this is because the constraints. We have so little data. So the way we evaluate this model, we have two phases of evaluation. The first one, we just create some synthetic data ourselves. So the way we create the synthetic data, we just random sample. So we use all real data. We don't create some artificial numbers. So we use real data, but you can think of we swap user behavior. So we target through some random sum process, or we create some attacker, and the random sum that attacker behavior can attack that as a positive, and create a positive negative data set, and then rank rank according to the anomaly score generated by the engine, and to see what's the precision recall there. So and then we draw the precision recall curve. So you all know, the ideal case will be the upper right corner, right? So the curve more push the upper right corner is better. So we do this, we do multiple sample and try to see what's the 95% confidence interval there. So you see like lots of curves there. So because there's random sample process, so we random sample multiple times. And with our business requirements, so you can see with the 40% of a recall rate, and the 95% of a precision interval is around 92 or 90. So it means that it satisfies our business requirement. But you can see the curve as a steep, so it's a very steep curve, right? Why is that? Because we swap user behavior, right? So sometimes, as I mentioned before, the user himself will do some non-typical stuff. So the precision will drop quite significantly if you want to include all the increase the recall rate. And then we deploy this model in our inside big cluster and actually scan the actual data. And this is the data, actual data. And the chart on the left-hand side, which is the x-axis, just data ID. And the y-axis, which is the score. And we do see some Euro stuff. So we compress the left-hand chart into one dimension, and you can see that's what the right chart looks like. So we see like there's one or two instances which have really large anomaly score, and we look into those. We look into the event or the log. We trigger that anomaly score, and indeed find some interesting scenarios. So the user himself is doing some Euro stuff, and internally we have very high business interest to further study those anomaly events. To summarize a little bit, so at Salesforce, so this anomaly detection engine actually is a generic platform. So we start with at our team, we use this to detect, users' anomaly, in-app behavior anomaly. But we scale, because the platform is generic enough, you can put as many features you want. And if you extract the relevant feature for you and build a profile. So this platform actually can be easily scaled to other problems. And actually, we are supporting other security team at Salesforce and to try to detect the anomaly at application layer. Yeah. So basically, this is all the things we want to share in this talk. Yeah. Any questions?
Thank you, guys.
So we have some time for questions. There is a mic right in the middle of the room for any questions.
Yeah, I was wondering if you could comment on the advantages that you see of this approach using PCA versus maybe some more standard methods like a Gaussian mixture model.
Yes, so we haven't compared, actually we didn't do experiment that, but the main reason we use PCA, which is for security, the main thing we care about, like we want to extract the user stable, which dimension user are very stable along that dimension. So that's the main reason we use PCA. Actually, it's very important for security. Yeah, that's the main reason we use PCA for this. Yeah.
So part of the main goal of this is that when a user comes in, makes some transaction, there's some sort of like on-the-fly machinery, right, making a prediction and raising a flag of sorts, right?
Mm-hmm.
Can you talk a little bit about how that process looks, the on-the-fly sort of like location of the user in this user space?
So in the production, so we have other two to first look at, which dimension, which raw feature has the most contribution to this anomaly score. So, and then we will quantify that. So basically have a feature importance array. So the process, we will further hand off all this information to our internal analytical team. And they will do other correlation, So because this anomaly only triggered by one particular event. And they will extract all the other information, maybe within the same session from the same user and try to correlate all the other information and to see, whether there's other suspicious stuff going on.
Yeah, if I can add to that comment. So as we see user, start doing certain things in the platform, those events will be logged in the system and will be streamed into the detection model. So the detection model itself already have the profiles built on that user. Or, in certain circumstances, this user might be a new user, just registered and just start logging in. So we probably do not have any history of this user. The way we deal with that is we have the natural organization of user groups. In our case, it would be like a business customer, a organization. So then we profile at that organization level, so we have the group level of behavior prediction. Then when we see a user's action or events, we'll be able to either evaluate this event with, just against this user's own history or his organization's group behavior history and make a prediction. And like we said, once the anomaly is being picked up, this is going to be sent to our security team for further evaluation. So the entire thing is not strictly in real time, but down the road, we are exposing these intelligence onto the customer UI. So the customer will have a chance to see such alerts and decide if this is something worth evaluation.
It's very interesting that you mentioned It's very interesting that you mentioned the legitimate anomaly, because we tried several anomaly detection models on the sensor data coming from the machines. And sometimes there are legitimate anomaly. For example, when we get the sensor data from large refrigeration data, they have really kind of a good pattern of defrost cycles. And when the temperature is really high, then it's really a legitimate anomaly, but not the true anomaly when the refrigeration breaks down. So we tried several methods, and one of them is like deep learning, and then it works pretty well, but it's very hard to scale, especially we're streaming the data, we're sending out alert to our customers. Can you elaborate a little bit more on how you differentiate between legitimate anomaly versus the real anomaly, how you tune your models?
Yeah, that is something like we constantly have to deal with. That is like for anomaly detection is always rare events, so there's no single model that can just give you that 100% confidence answer. This is truly a malicious or suspicious or anything of interest. So in general, the way we've been dealing with is we correlate it with additional information. So we have anomalies picked up here, but we also have other places. We have other type of models to look at different patterns or characteristics in the system. At the same time, I think we can probably talk about the feedback loop that we're designing and prototyping.
So actually, okay, hear me? Yeah. So this engine only can tell you what's something usual or unusual, right? So this engine doesn't understand, so unusual stuff not necessarily mean threats, right? So you have some other, you have some model in the second layer. Once we have some feedback, actually we are building that, so we will learn, and the worst scenario, this unusual scenario actually indicate a threat. And what other scenario actually is not, it just uses his own typical stuff. So you can think about there's two layers of the model. The one layer just detect unusual stuff, have very generic capability to detect to find patient zero, right? And there are model in the second layer. We'll learn some feedback and to understand, those anomaly. To further extract pattern from those unusual scenarios. Yeah.
It's probably really hard to determine because you're looking for unknown unknowns, but do you think there are specific security use cases in which this model really excels and other use cases in which you think that you're weaker?
Yeah, we can. We probably cannot get into a specific attack scenario that has happened on our platform. It's just because it's more of like a sensitive topic. I think it will be a better idea that we can reach out through email, and we can definitely, get into more detail of that.
So you mentioned that you use synthetic data to fit the model. Can you elaborate a bit about how you generate the synthetic data?
Mm-hmm. Yeah, so the basic idea is just swap user behavior, right? So we first, for example, for a given user, and we first create our attacker for this user by random sample, through some random process. And then we just, another random process, we will random sample that attacker's data and can attack that as a positive, give a positive tag. And then, change the user ID. Just think this belongs to the same user. And so basically create that positive and negative data set. And then try to see whether anomaly score can notify that actually this behavior is come from different user.
As a follow-up to this, in creating that data set, what kind of distribution do you have of negative and positive samples? And does it represent reality? Because if you look at real data streams, the percentage of actual security events is way small, which is hard to train. How do you manage that bias?
Actually, we are not really working with positive data. we have so little, so there isn't much like we can really work with. So eventually, in the feedback, whatever optimizing loop, we are expecting to collect more and more positive data, but right now the methodology entirely just reside in the anomaly detection field. And all we are observing or trying to compare certain events to is just the user or OI level historical distribution.
Do you mind talking a little bit more about the process that you guys took to build out the feedback loop, how to collect data, such as like what problems you run into? You guys don't have to dive into any proprietary information, but just the general process.
So the feedback loop actually is not easy, right? So as we deploy a model, it's an evolving process. So at day 0, the day after you deploy this model, you may expect so there are 3 different scenarios. The first scenario, at day 0, you may receive lots of false alarms. And you have technique targeting, deal with that scenario. And day 1, the model improved, and you may see a little positive sample. And then we have another model for dealing with that cases. And after day N, the model mature enough, and then you see a reasonable rate of positive, a reasonable positive rate. So the 3 different scenarios actually we have 3 different objectives for the 3 scenarios. So for example, at day 0, the day we receive lots of false alarms, then we have some techniques, So basically it means that we have made this mistake and don't mistake again. So we have some other technique, and we'll learn those false alarms, and then if we see the similar one under some statistical measure, and then we don't assign the similar anymore. It's an evolving process, so it's not that one model take care of all. Yeah.
Okay, so that'll be the end of questions. Let's all give another round of applause for Ping and Wei.